Thanks to the proliferation of the internet, online advertising has emerged as a multi-billion industry. Online advertising aims to efficiently allocate the resource of ad impressions for advertisers and resorts to the mechanisms of online auctions. In these repeated auctions, modern advertisers often rely on software agents to optimize for their long-term utility on their behalf. To fulfill the diverse demands of different advertisers, the goal of the software agents is to employ effective bidding strategies that optimize the advertiser's objectives subject to their spending constraints. Existing approaches on constrained bidding typically rely on IID train and test conditions. This contradicts the adversarial nature of online ad markets because different parties involved in the auctions have potentially conflicting objectives. For example, sellers seek to increase their revenue, which turns out to be the advertiser's cost. Rival buyers aim to obtain more exposure, which in turn reduces our exposure. In this regard, we explore the problem of constrained bidding in adversarial bidding environments, which assumes no knowledge about how the adversarial factors perturb the bidding environments. Instead of relying on the IID assumption, our insight is to align the train distribution of environments with the potential test distribution, and then optimize the policy under such train distribution. Based on this insight, we first aim to mathematically formulate the potential test distribution. Our intuition is that, if the policy performs worse in an environment, then the environment is more likely to appear during test. To this end, we use the notion of regret to measure the performance gap of the policy with respect to the optimal expert policy, and then define an energy-based distribution as the test distribution, which is proportional to the policy performance measure, the regret. Given the potential test distribution, we first find an aligning train distribution in the train environments by projecting the distribution into the train set in terms of KL divergence. Under this train distribution, we then optimize the policy through regret minimization. This results in a Minimax regret optimization framework, namely Mi-Roll, which interleaves between a teacher finding adversarial environments for tutoring and a learner meta-learning its policy over the given distribution of environments. While this crude version of Miro appears appealing, we discover several practical limitations. Firstly, the Minimax game is not intractable due to the unknown structure of the environments and the adversarial factors. Therefore, we propose a practical algorithm that renders a differentiable game, which can be optimized end-to-end. In addition, regret minimization aims to minimize the gap between the policy and the expert. However, Mi-Roll degenerates to value maximization problem without expert taking effect. Motivated by regret minimization, we pioneer to explicitly leverage the expert demonstrations for learning bidding strategies. Through a causal lens, we first identify that the straightforward behavioral cloning approach suffers from the unobserved confounding issue. To address this issue, we propose a causality-aware approach, which can effectively improve upon Mi-Roll by distilling knowledge from the experts. Our approach is dubbed Miracle for Mi-Roll with causality-aware reinforcement learning. Thank you for watching.